Hello everyone. My name is Umameshwar Reddy Alwala, and today I will be presenting my hypothetical research paper titled "Energy Aware Cognitive Layer Optimization for Green Semantic Communication Networks." This is my agenda: introduction, problem statement, and objectives, literature review, proposed methodology, flowchart of proposed method, expected results and discussion, and finally conclusion and future work. Introduction. In semantic communications network, the cognitive layer plays a major role. It senses the environment, interprets the raw data, extracts knowledge, and extrapolates raw data, and decides what information actually need to be shared. Because of this, the cognitive layer is continuously active um, and consumes energy, especially in IoT devices, drones, and autonomous vehicles. And the survey paper semantic communication networks, including the control layer, transmission layer, and cognitive sensing layer. However, even though the paper briefly highlighted the high energy and cost of cognitive operations, it didn't provide any concentrate mechanism to address it. And next one is problem statement and objectives. The core problem you addressed in that the cognitive sensing layer in semantic communication systems consumes a lot of energy. It continuously collects data, runs inference models, and uploads knowledge bases, even when information is not important. Most existing research focuses on optimizing semantic encoders or improving transmission efficiency. However, the energy behavior of the cognitive layer itself is often treated as fixed. This creates a major bottleneck for battery-powered devices. So the study proposes three main objectives. One is to develop an analytical energy model that represents the sensing, processing, and communications cost at the cognitive layer. To design an energy-aware control mechanism that dynamically adjusts sensing rate, resolution, offloading decisions, and update frequency. To evaluate the approach through simulations and compare it with the traditional always on cognitive layer. By meeting these three objectives, the system can reduce energy use while still maintaining semantic accuracy and knowledge freshness. And next slide is literature review table. Before proposing the solution, I reviewed at least 10 papers published between 2023 to 25. And these papers cover semantic communication architectures, cognitive frameworks, semantic metrics, green communication techniques, and energy efficiency, energy efficiency optimization approaches. Across these works, there were two key observations. First, most studies focus on optimizing the semantic encoders, decoder, or the physical layer, leaving the cognitive layer almost unchanged. The second one, several papers mention the importance of reducing computational cost, but none of them formulate a full optimization model for the cognitive sensing layer. This clearly shows a research gap that my hypothetical case study aims to fulfill. And the next one is proposed methodology. My methodology is simulation based and primarily quantitative. I model I model a multi-agent semantic communication network where each agent has sensors, local AL models, and a communication model. The system follows a cloud edge device architecture. Agents process simple tasks locally, but but I can offload heavier workloads to the edge server. The proposed method has five main components. One is energy modeling, sensing every depends on the duty cycle and duration. Processing energy depends on the complexity of the neutral network used for semantic extraction. Communication energy depends on the size of the semantic fragments sent. And second one is cognitive cognitive control parameters. Sensing rate, semantic evolution level, local versus edge processing, knowledge update frequency, and third one is reinforcement data learning module. An RL agent makes real-time decisions based on battery level, channel processing, and task urgency. Baselines for comparison, always on cognitive layer. Simple threshold energy saving method, proposed RL based adaptive method, data sets, autonomous driving tracks or IoT sensing data sets are used to simulate real world scenarios. The final output of the methodology is system that can intelligently reduce energy consumption without compromising accuracy. Next one, flowchart or proposed method. This flowchart shows the end-to-end processing. The system starts with environment sensing, where the device collects raw multimodal data. Next, semantic feature extraction converts the raw data into meaningful information using AL models. The most important block is the energy awareness decision module. This RL-based controller dynamically decides how often to sense, what resolution or of semantics can generate, whether to process locally or offload offload to edge, where to send knowledge updates. The decision directly impacts energy consumption. After decisions are made, the system processes tasks either locally or at the edge. Finally, on only high value or time critical semantic updates are sent to the knowledge issues. So this pipeline ensures ensure the energy is used only with the necessary. Next one, expected results and discussion. Based on preliminary analysis and insights from related work, several expected outputs can be anticipated. Energy reduction. The energy aware policy will significantly reduce total energy consumption by selectively considering sensing frequency and batching knowledge updates. Maintained accuracy. Since accuracy constraints are included in the optimization, semantic performance is expanded to remain within acceptable limits. Improved battery lifetime. Battery powered devices like IoT sensors, UAVs, and mobile keyboards can operate longer without charging. Trade-offs. The study will reveal a clear trade-off between the energy saving, and timeliness of knowledge updates. And the last one, better scalability. With hierarchical coordination through the control layer, system-wide performance improves, especially in multi-agent settings. And the next one is conclusion and future work. To conclude, the hypothetical study addresses an important gap in semantic communication research. While many prior works optimize encoders or transmission methods, the cognitive layer where sensing and interpretation occurs remains energy hungry. This research proposes a dynamic energy awareness optimization framework that reduces redundant cognitive operations while protecting semantic accuracy. The reinforcement learning approach adapts to real-time conditions and allows devices to operate efficiently in green semantic networks. In terms of future work, the study can be expanded by integrating detailed hardware models like specialized AL accelerators adding privacy and security constraints, implementing the framework in real world test beds instead of simulation, implementing the framework in real time test beds instead of simulation, combining cognitive optimization with advanced semantic metrics and cross modal knowledge gaps. Thank you for listening and thank you.